Hello and welcome to intypedia. Today we will explain the basics of the SSL TLS encryption protocol, a very important protocol for electronic commerce and secure virtual private networks. This is a very interesting topic. Come along.
In the 90s, the company Netscape Communication, famous for making the Netscape Navigator web browser, created and developed a method for providing secure communications over a network, the SSL Secure Sockets Layer Standard Protocol.
This protocol is very useful because when we surf the internet, many attacks can be made to the exchanged information, integrity and confidentiality, as well as attacks to the identity of persons or services. We connect to authentication, as we saw in Lesson 4.
That's right. In such cases, the use of the SSL protocol is very helpful. Unfortunately, it isn't always implemented, and when users don't use it properly, it's easier to perform attacks without having to change the security measures defined therein. In telecommunication networks, like the Internet, these attacks are usually carried out through man-in-the-middle attacks, MITM. When integrity and authenticity procedures aren't enabled, it's possible to change or modify the information in transit and also to impersonate the sender or receiver of the communication. Nowadays, such attacks are very easy to carry out using free tools available on the Internet. A recent man-in-the-middle attack famous for the publication of the Handshake tool consists of stealing a user's session cookie, the one that authenticates when the user logs into a web service like Facebook, Twitter or a Google account.
Wow, and how is that possible?
It's possible when the attacker has access to the exchange traffic, when they are in the same wireless network, for example, and when the data can be read easily. Once they have the session cookie that authenticates the user, they can impersonate the user and enter the sites that this validation provides access to. The attack based on stealing a session cookie, the HTTP session hijacking attack, has been known for a long time, but the Handshake tool, a Firefox browser extension developed by Eric Butler in October 2010, shows that these attacks are very common nowadays. Interestingly, this incident prompted some companies to enable the SSL protocol for accessing their services securely. A significant example of this was Facebook. Maybe they hadn't considered it before because of its complexity, cost, and that it would slow down the communications.
How fascinating. So how does this protocol work?
Interesting question, Alice. Now we are going to explain it in detail. SSL Secure Sockets Layer is a cryptographic protocol that provides authentication, integrity and confidentiality of the information in a client-server communication over a network, like the Internet. It runs in a layer between the application protocols such as HTTP, SMTP or NNTP and the TCP transport protocol. Today it is also possible to implement it on UDP. Usually, it is configured so that the communication server is authenticated while the client remains unauthenticated. This is typical, for example, when we connect to our bank's online website through HTTPS, where the S for security means that the SSL protocol is being used. Mutual authentication of client and server is also possible using this protocol.
I have a question, Bob. I've heard that a protocol called TLS is also used for these purposes. Are SSL and TLS the same thing?
Good question, Alice, because many people are confused about this. The SSL protocol has been the basis for developing the TLS, Transport Layer Security, protocol, currently in version 1.2, also known as SSL 3.3, defined in RFC 5246. SSL and TLS are conceptually similar, only that TLS enhances the classic SSL in some aspects, such as protecting against further attacks, providing new cryptographic algorithms, avoiding the forced use of more vulnerable versions of the protocol, and so on. Apart from agreeing on the version of the protocol, in order to establish the communication with the integrity, confidentiality and authenticity requirements, it is also necessary to agree in advance upon the security parameters that will enable a secure communication. These phases are performed by the SSL/TLS handshake protocol. However, we mustn't forget about another important protocol, the SSL/TLS record protocol, that specifies how to encapsulate the sent and received data, and even the negotiation data.
I see you've studied the subject. Could you explain how the SSL handshake protocol works?
This protocol focuses on three things. First, the client and server negotiation of the algorithms that will be used in the communication. Some of the cryptographic algorithms used for encryption, key exchange and signing are 3DES, IDEA, AES, RSA, Diffie-Hellman, DSA, SHA-2. Second, the exchange of keys and the authentication based on digital certificates, using, whenever necessary, a validation through public key infrastructure (PKI). And third, the encryption of traffic using symmetric cryptography. A session key is generated for communication based on the negotiated parameters, thus enabling the encryption of the data. As mentioned in previous lessons, symmetric cryptography is fast and requires less hardware resources, which is ideal when it is running on client, which usually has fewer resources than the server. Asymmetric cryptography is only used for key exchange and signing. Therefore, this protocol is a good example of the usefulness of hybrid ciphering. The secure connection begins once the parameters have been negotiated, but if the negotiation fails on any of its stages, the connection is cancelled. Let's take a look at an example, where only the server is authenticated by its certificate. The following are the most important messages exchanged in the negotiation until the communication is established by means of a simple TLS handshake. 1. The client sends a client hello message specifying the highest TLS protocol version it supports, a random number and a list of authentication, ciphering, MAC, message authentication code, and compression algorithms. 2. The server responds with a server hello message, containing the selected protocol version the highest supported by client and server, a random number, the chosen algorithms from those sent by the client, and its digital certificate, using a certificate message to authenticate itself. 3. The client verifies the server's certificate through a trusted authority or a PKI. Then, the client answers with a client key exchange message containing a pre-master secret, a secret number, with the information to generate the session key. If the RSA algorithm is used, the message will be encrypted with the server's public key and the random number generated by the client will have 48 bytes. 4. The client and server use the exchanged random numbers and the pre-master secret, retrieved by the server using its private key. With this data they compute a common secret called the master secret. All the keys for this connection are derived from the master secret by means of the established pseudorandom function. 5. The client now sends a change cipher spec record, and tells the server that from that moment on, all the exchanged information will be authenticated, and if established previously by the server it will also be encrypted. 6. Finally, the client sends a signed and encrypted finished message, containing a hash and MAC of the message as negotiated previously. 7. The server then decrypts the finished message sent by the client and verifies the hash and MAC. If the decryption or verification fails, the connection doesn't go through. 8. If everything goes well, the server sends a change cipher spec to the client indicating that, from that moment on, everything it sends will be signed and, if encryption was previously negotiated, encrypted. The server then sends a signed and encrypted finished message containing a hash and MAC of the message as negotiated previously, which is then validated by the client. 9. The negotiation phase ends and the client and server can now exchange authenticated and encrypted, if encryption was negotiated messages.
How interesting. And all of this is done in a transparent way for the user.
There is no doubt that the success of the SSL/TLS protocol is due to the expansion of electronic commerce on the Internet. Most financial institutions advocate its use, Visa, MasterCard, and American Express, just to name a few. Today it is hard to think of secure Internet communications without the use of SSL, digital certificates and public key infrastructures. A clear example is the securing of web traffic, where HTTPS is used instead of HTTP. SSL can also be used to tunnel an entire network and create a virtual private network VPN. This can be achieved with the open software tool OpenVPN. For instance, it provides a point-to-point connection with hierarchical validation of remotely connected users and hosts. Among other benefits, it is also widely used to provide authentication and encryption in voice over IP traffic VoIP, that is, voice transmitted over the Internet using the IP network protocol.
From what you have told me, I understand that since the SSL protocol is above the transport layer and below the application layer, with this protocol it would be possible to secure the communication between any software. But I have some doubts. If my company wanted to develop an e-commerce website, how could I establish this protocol on my server? Could I do this on my own, or would I have to buy it from a company? How are the exchange keys and the digital certificate generated? How do I install it?
Well, there are several ways to do this. If we focus exclusively on open technologies, you would only need the Apache web server, the mod SSL and the Open SSL software for your purpose. Even if you wanted to authenticate the clients that connect with X509 digital certificates, once all the software is installed and configured, the server and the client's web browser will be in charge of all the cryptographic process. That would be a broad enough topic to take up another lesson, but there is much information about it on the Internet in case you want to learn more about it.
Bob, is it possible to cancel out the security provided by the SSL/TLS protocol?
In general, we can say that the SSL/TLS protocol is rather secure, although it obviously depends on the version of the protocol and its implementation. Today, the latest version of the TLS protocol with its recommended extensions is considered to be secure. It avoids request injection attacks that force the protocol to perform inappropriate actions or the renegotiation of parameters that undermine the security of the established secure channel. In practice, enabled cryptographic procedures are not subject to attacks nowadays, because it isn't that easy to perform attacks on them. These procedures are based on publicly contrasted algorithms, and a failure in the algorithms would be corrected by updating the protocol to more robust algorithms. Today's attacks focus mainly on tricking the user, especially if their computer is controlled by a Trojan, or taking advantage of software misconfigurations. Usually, they try to make the user think they have an encrypted communication when they don't. For example, simulating the lock seen in safe websites, making users accept digital certificates that are not valid for the server they want to connect to, forcing the use of different versions of the protocol or cryptographic algorithms with a known weakness downgrade, and so on. Don't be surprised that many people have trusted for years, and continue today, to rely on the security of a website simply because they can see the lock icon. In the following lesson we will take a look at the best known attacks to breach the security of the SSL protocol.
Bob, I wouldn't like to wait until the next lesson to know how I can connect to my bank in a secure way.
Of course, Alice. It's not that complicated. As you know, the use of SSL is vital for a secure access to e-government services or online banking. A first recommendation would be to write the URL directly with the HTTPS prefix in the address bar of your browser. Then, if the browser indicates that the digital certificate of the entity we want to connect to is not recognized or that it isn't valid, do not accept it under any circumstances and the connection will not take place. As an additional measure, and going quite to the extreme, you could verify the signature of the digital certificate of the server you are connecting to, if you have written it down previously, looking at the web browser. If you want to, you can install tools that always force HTTPS connections, like the Firefox browser extension HTTPS everywhere. Also, you should configure your browser properly so that the OCSP, Online Certificate Status Protocol, denies revoked digital certificates. Furthermore, if you're interested in analyzing the security of SSL technology in a specific server, you can start by studying the free documentation published by the OWASP, the Open Web Application Security Project. For example, the Testing for SSL TLS tutorial.
Great! I think this is enough for today. In the following lesson we will continue with this very interesting topic. At intypedia you can find additional information for this lesson. Goodbye.
See you soon.